Alright, welcome back to Organic Chemistry. In this unit we're going to look at conjugated pi bonds. I'll define what conjugated means in a moment. It means a pattern of alternating double and single bonds. And we're going to focus in on acyclic systems. Things that have a ring of double and single bonds, the aromatic systems, are going to be our next unit. But here we'll just focus on things that are long chains of multiple pi bonds. I'm going to break this into 3 separate presentations for the sake of the size of the video. The first will look on what does it mean to be conjugated and what are sort of the orbitals involved and how are those, what's the consequence of conjugation. In the second and third sections of this video, I will look at the reactions of conjugated pi systems. Start out with some definition. Conjugation is essentially when I have patterns of alternating double and single bonds. So for instance, this system is conjugated and this system is not conjugated, because here my pi bonds are adjacent to each other and here they're not. So I have to have multiple pi bonds that are next to each other to have conjugation. Suggested on the previous slide, I also will look at acyclic conjugation versus cyclic conjugation. We'll talk about cyclic conjugation later. So let's start out by just grabbing some data. If I took 1,4-hexadiene and I hydrogenated it with hydrogen and palladium, we know what will happen. Pi bonds react with hydrogen to make single bonds. When I take 1,3-pentadiene, did I say hexa? I meant penta. 1,3-pentadiene and do the exact same reaction, the same thing will happen. And in both I make the same product, pentane. I can go into a lab and figure out the energies of these, and I shouldn't expect them to be identical because they start from different places, and they're not. Both downhill. That is, in both cases I go from a higher energy point to a lower energy point. My delta H is negative. But this one is more negative, which means I start at a higher energy place than this one. That means I can compare this system, which is not conjugated, to this system, which is conjugated, and I find that the conjugated system is lower energy. This turns out to be generally true. That's our first piece of data. Conjugated systems seem to be more stable than non-conjugated systems. Our second piece of data has to do with bond length. Single bonds, double bonds, and triple bonds are different in length. As a general rule, single bonds are longer and multiple bonds are shorter. Okay. If I look at butadiene, 1,3-butadiene, the bond between the second and third carbon, well, it's shorter than other just alkyl single bonds. So that's our second piece of data. This bond length is kind of somewhere between a single and double bond. It's still a single bond, but it's shorter than other single bonds. Alright, third piece of data, conformations. So this would help if you pulled out your model set and built a model of butadiene and realized that you can rotate around the central carbon-carbon bond, the 2,3 bond, and you could go from a all trans, all coplanar conformation and rotate around that bond to go from sort of an eclipse to a staggered to an eclipse to a staggered. I can draw Newman projections if I put my eyeball up here and look down the 2,3 bond. Projections just like we did with alkane rotations. Notice there's really 4 important conformations because as I rotate around I'll go from, let's keep the front the same and rotate the back. Go from an eclipsed, go 90 degrees to a staggered, another 90 degrees to an eclipsed, to a staggered, and then if I was to keep going, I'd come back around to where I started. Now you might recall from the first semester of organic, we did this sort of thing with alkanes, and the staggereds were always the high energy points, and the eclipsed were always the low energy points. And between those, we could also say that, things that brought bigger groups closer together were higher in energy than the ones that didn't. So for instance, I compare this maximum to this maxima to this maxima, this high point to this high point, and say they're different, and I compare this low point to this low point, and they're different. But that's secondary to the fact that the eclipsed are high and the staggereds are low. But if I did the experiment with this butadiene, I would find out that the eclipsed conformations are the low energy points and the staggereds are the high energy points. Now there's a difference between these in that this eclipsed conformation is more stable than this one, but still they're the minima and these guys are the maxima. First and third have names. The first one's called the S-trans conformation and the third is called the S-cis. That is, this group and this group are trans with respect to an intervening single bond or sigma bond. That's trans with respect to the S. And these two groups are cis with respect to that intervening single bond. Okay, to explain this data, we're going to consider the orbitals. And we're actually going to focus in on just the p orbitals. Huckel is a guy who was interested in these pi systems, did a lot of key work. We're going to come back to learning about him again. And he said, let's only consider the pi bonds, only the p's, pi's, and pi stars. Because those are going to be the interesting ones. Those are going to be the highest occupied molecular orbitals because in general, sigma combinations are very low energy, and then come pi's, and then come pi stars, and then sigma stars are very high. So the pi's and pi stars are in the middle, and those are the most interesting to us, because if I'm going to take electrons away from something or put electrons into something, I'm going to be focused on those. The sigmas don't interact with the pi's, because the sigmas are in the node of the p orbitals, so we can pretty much ignore the sigmas. Huckel also said, let's consider only interactions between adjacent positions. So he ignored any long-range interactions. You could have an extended Huckel theory where you consider long-range interactions, but we're just going to stick with a simple consideration where we just say things interact if they're on adjacent positions. Now Huckel, when he initially did his work, it was kind of all on paper. And so he didn't have the energy of a p orbital. So he just said, let's call that something. Let's call that alpha. So alpha is just a constant. And he said, when two p orbitals interact to make a pi bond, we're going to call the strength of that interaction beta. Again, it's just a constant. There's an actual value to that. We can now go out and measure those things and get the values that Huckel didn't have. But it's easier mathematically to just treat them as constants. They're negative constants. That's going to make the signs on the math come out right. So all you need to know about beta and alpha are they're both constants and they're both negative numbers. We're going to use these things to calculate something called the pi energy. And that's going to be defined as the total energy of all the electrons in the p, pi, and pi star orbitals. So again, we're ignoring any sigma bonds, and we're just going to consider the energy of those electrons. Okay, so what the heck do I mean by this? Let's add something simple that we all know. If I take two p orbitals and bring them together, they will combine in bonding and anti-bonding ways to make pi and pi star combinations. Using Huckel's terminology, separate p orbitals are at energy level alpha. If I bring them together, the interaction between them is going to have the strength of beta. That is, this guy is going to be lower energy, and this guy is going to be higher energy by beta. Beta is a negative number, so if I add beta, I'm going to a more stable orbital energy level. If I'm subtracting beta, I'm going to a higher energy level. The total pi energy of these things is going to be the total energy of the electrons, either in two separate p orbitals or in this combination. And let's compare. Using Huckel's terminology, if I've got two separate p orbitals, let's say I've got one electron in this orbital and one electron in this orbital, they're both at energy level alpha. On the other hand, for ethene, where are those electrons? They're here, a lower energy. And let's say that they're both in an orbital that has the energy level alpha plus beta, and so the total energy is 2 alpha plus 2 beta. Since beta is a negative number, this is a lower overall energy than this. Things are more stable when they're double bonds than when they're two separate radicals. Okay, so far so good. You already knew all that. Something a little bit different. Let's look at an allyl system. An allyl system, cation, radical, or anion, all, involves a reactive intermediate adjacent to a pi bond. And we know, we've talked about these in context of resonance, that I can draw resonance forms where this electron shares with this to make a pi bond here, and then I'd have a radical over here. Or if this was a cation, I could do it with a cation over there, or an anion as well. Now, to get this resonance stabilized thing, I have to have orbitals that can interact on all three positions. And so I'm going to have p orbital here and here, because a pi bond is made up of two p orbitals, and my radical here is going to have a p orbital. So I've got three p orbitals in a row. Huckel said we can consider just the pi system, just the p orbitals, and if I have a total of 3 p orbitals, I'm going to combine those to make 3 combinations. We know that from when we initially talked about orbitals. If I'm going to put together 3 p orbitals, all that's really going to differ is the phases, that is the shadeds and unshadeds. And if things are in phase, that's going to be stabilizing. So the lowest energy combination is going to be the most bonding, the most in phase. On the other hand, if I had nodes, a node is a place where you change phases, I'm going to be higher in energy because nodes are associated with antibonding. So if this one has 0 nodes, the next orbital is going to have 1 node. So let's put 1 node in. I'm going to put it as symmetrically as possible. If I put it right here, I'm going to change phases, so I'm going to go from shaded on the top to shaded on the bottom. But a node is where electron density isn't, so if my node is right in the middle, there's not going to be any electron density there. My second orbital up is going to look kind of like this, 2 separate p orbitals with an empty space in between them. And then if I go to something that's got 2 nodes, I'm going to symmetrically as possible, so I'm going to put 1 over here and 1 over here. And notice I switch phases. Notice this one's all bonding, and this one's all anti-bonding, and this one's somewhere in between. And Huckel's actually able to calculate the energy of these as alpha plus 1.41 beta, alpha, and alpha minus 1.41 beta. Let's first consider this. Huckel said let's only consider the interaction between adjacent positions. And remember, there's a carbon with no p orbital here because my node went through there. So these are just really 2 separate p orbitals. This one, it's got bonding, and notice it's more bonding than ethene because there's 2 favorable overlaps. Now it's not twice as much because this one is actually interacting both with this and with this, so it's not giving its full attention to either one. So it's not like I got twice a beta, as it were. But Huckel's able to calculate these energies and come up with an overall orbital energy for this. Okay. Let's consider the resonance stabilized allyl reactive intermediate, carbocation, radical, and anion. If I've got a carbocation, what do I have? I've got a pi bond and an empty p orbital. So I've got a pi system, 3 p orbitals, these 3 p orbitals, with a total of 2 electrons in the pi bond, in the pi system, because I got 2 for the double bond and 0 for the carbocation. So I have these set of 3 p orbitals, and I got a total of 2 electrons, and they end up in the lowest energy orbital. I had an allo radical, resonance stabilized allo radical. I've got the same set of p orbitals, 2 here and 1 here. There's 2 electrons for the double bond and 1 electron for the radical. So I'm going to have the same orbitals but with a different occupancy. That is 2 electrons here and 1 there. The resonance stabilized carbanion, to be resonance stabilized, for this pair of electrons to interact with that to make a pi bond, this has to also be sp2 hybridized. And in that case, I've got 3 p orbitals on these 3 positions. Same combination of 3 p orbitals, but a total of 4 electrons within the pi system. And so if I fill in electrons, 2 will go in the lowest energy, and then the next 2 go in the next, and then I'm used them up. I get this orbital occupancy. So for these resonance stabilized species, I have the same set of orbitals, I just have a different total number of electrons shared across those orbitals. All right, let's consider the energies of these. Remember I said we can calculate the pi energy as the energy of all the electrons in p, pi, and pi star orbitals. So let's consider the allocation. Here I've got 3 carbons, and focusing on the pi electrons, I got a total of 2 electrons. I could imagine that as 3 separate carbons, 2 radicals and 1 carbocation. Or let's imagine combining these guys to make a double bond, and then I've got a carbocation. Or let's imagine combining them all 3 to make the resonance stabilized allocarbocation. For the first case, we've got 2 electrons at the energy level alpha, because this electron's in a p orbital at energy level alpha, and this electron is in a p orbital at energy level alpha. It's 2 alpha. For this guy, what do I have? I've got 2 electrons in a pi bond and 0 electrons here. What we would say is we have 2 electrons at energy level alpha plus beta and 0 electrons at energy level alpha. 2 alpha plus 2 beta. Okay, for the allocation, I've got, remember, this set of 3 p orbitals, but I've got a total of 2 electrons in the energy level, the orbital that has the lowest energy orbital, that has the energy level alpha plus 1.4 beta. I got 0 electrons in the next and 0 electrons in the next. I didn't even show the third. In other words, the total pi energy of this is 2 alpha plus 2.8 beta. Notice my resonance stabilized thing is more stabilized than just a carbocation and a pi bond that aren't in resonance. Okay, that's probably unsurprising, because I did use the term resonance stabilized, and now I've concluded that it's stabilized. So, okay, not that exciting a conclusion, I suppose. We could look at radical, but we can make the exact same argument. Here I'm considering 3 separate carbon radicals. Each of these electrons is at energy level alpha. Here I've got 2 electrons in a pi bond and 1 electron in a carbon radical. So 2 electrons at this energy level and 1 at this energy level. And then if I have the resonance stabilized allo radical, remember I had that same set of p orbitals, this energy level, this energy, and the one that I'm not showing, 2 electrons in the lowest energy one and 1 electron in the next. And again, notice I am more stable conjugated than not. Finally, I can make the same argument for the allo anion. Again, more stable conjugated than not conjugated. You can go through and do the math yourself, but in each case we see a greater stability, lower energy, due to conjugation. Now again, these are all resonance stabilized. These are carbocations, radicals, and anions. They're reactive intermediates that are stabilized by resonance. So that we've concluded that they're more stable is, well, that's just restating the obvious. Let's consider, on the other hand, butadiene. Butadiene it doesn't have a carbocation or anything like that. But let's consider the orbitals. We've got 4 sp2 hybridized carbons in a row. And so Huckel would say that let's just consider this as a set of 4 p orbitals in conjugation. And the lowest energy combination of, we're going to make 4 combinations. The lowest energy one always has all in phase. As I increase the number of nodes, I'm going to increase energy. So here I'm going from 0 nodes to 1 node to 2 nodes to 3 nodes. I'm going from 3 bonding interactions to 2 bonding and 1 anti to 1 bonding and 2 anti-bonding to 0 bonding and 3 anti-bonding. Huckel allows us to calculate the energies of those orbitals without going through how he did that. Here's what the conclusion is. Notice that these energies are kind of symmetric in that this is stabilized by the same amount that this is destabilized by. And we could fill in electrons, say that these guys are full and these guys are empty because I have a total of 4 electrons within the pi system. All right, let's do this to this conjugated butadiene to 4 separate carbon radicals and to 2 separate alkenes. 4 separate carbon radicals have 4 electrons each in a p orbital. Total of 4 alpha. The pi energy is total of the energy of all those 4 electrons. If I looked at 2 ethenes, the total pi energy is the pi energy of an ethene plus the pi energy of another ethene. We know that the pi energy of an ethene, those electrons are this 2 electrons at energy level alpha plus beta, and 2 more electrons at energy level alpha plus beta. That's a total of 4 alpha plus 4 beta. That comes from our previous discussion of the energy of ethene orbitals. Now we've got butadiene. I've got 2 electrons at this energy and 2 electrons at this energy. Calculate. I find it that the total pi energy is 4 alpha plus 4.48 beta. Okay, going from radicals to alkenes, we got more stable. That makes complete sense because you wouldn't expect radicals to be as stable as, things with full octets, as it were. But here, going from 2 alkenes to a conjugated butadiene, we get more stable. Now that's interesting, because here we found out that a conjugated system, now this isn't a resonance stabilized carbocation or anything like this, but still, in acyclic species, and we'll contrast that later on with cyclic, but in acyclic molecules, more conjugation, or conjugation is more stable than not conjugation. Okay? Butadiene is more stable than 2 separate alkenes. Also notice that with this orbital has some amount of double bond character between these 2 positions. This one does not, but here we see a pi overlap. And then finally, note that to have this conjugation, all these p orbitals have to line up. That explains the data that we saw previously. We saw, for instance, that the conjugated system was more stable than the non-conjugated system. That fits our data, because we saw the heats of hydrogenation. We saw on the previous page that the orbital overlap between these 2 positions was a little bit like a double bond. And here we see that that's a shorter bond. There's some shortness due to that conjugation. And we also said on the previous slide that we had to have all the p orbitals line up to get that conjugation, and all the p orbitals line up when we have this coplanar conformation. When we have the staggered conformation, the p orbitals don't line up, and we don't get conjugation. That's like going from something like this to something like this that's not conjugated. Let's just go one more. We talked about ethene. We talked about butadiene. Let's go to hexatriene. This has 6 sp2 hybridized carbons. So there's 6 p orbitals, and Huckel would say, let's just imagine p orbitals. And there's going to be 6 combinations of those 6 p orbitals. And the lowest energy arrangement is going to be all in phase. I'm going to get to higher and higher level energy orbitals. Notice I'm going from 5 bonding interactions to 4 bonding, 2 here and 2 here. So between here and here, between here and here, and then 1 anti. So 4 bonding, 1 anti. 3 bonding, 2 anti. 2 bonding, 3 anti. 1 bonding, 4 anti, and 5 anti-bonding. So I'm going from the most bonding to the most anti-bonding. And the energy similarly reflect this. I have a total of 6 electrons within this set of pi orbitals, and so the bottom 3 orbitals will be full. Okay. Let's look at the energies of these. Let's consider 3 ethenes, let's consider a butadiene, and let's consider a hexatriene. So we already know that the energy level of an ethene, the pi energy, has to do with 2 electrons within an orbital at energy level alpha plus beta. So the total for this is, well, 6 times alpha plus beta, because I got 2 pi electrons in this one, in that orbital, 2 for this and 2 for this. 6 beta. We already calculated the pi energy of of butadiene and of ethene. And butadiene pi energy was 2 electrons at an orbital energy level alpha plus 1.62 beta, and 2 at an energy level of alpha plus 0.62 beta. And then we got the ethene, 2 electrons at an energy level alpha plus beta, up to 6 alpha plus 6.48 beta. All right, we already knew from our previous discussion that it was better to put 2 alkenes into conjugation than separate, so comparing this to this makes total sense. But if we look at hexatriene, we have 2 electrons at this energy, 2 electrons at this, and 2 electrons at this. And if we do all the math, that works out to 6 alpha plus 7 beta. So notice conjugation was better than not conjugation, so going from here to here, but more conjugation is even better. Okay, so this will be generally true with conjugated, acyclic conjugated systems more conjugation is going to lead to lower energy arrangements for your electron. All right, so we've looked at a series of conjugated pi systems, just starting with ethene, I guess that's not really conjugated, to butadiene to hexatriene. And you'll notice we get all these orbitals, and we could go on and look at 8, 10, 12, whatever. But what's most interesting to us are going to be, well, these orbitals are filled and these orbitals are empty, but the most interesting one are actually these guys and these guys. When we talk about an atom, we talk about the valence shell, right? If an atom is going to donate electrons to somebody else, they're going to come out of the valence shell, and if I'm going to add electrons in, they're going to go into the valence shell. What is that? That's the highest energy electrons and the next available empty place to put electrons. When we talk about molecules, that's also true. We're often concerned with the highest energy orbitals that have any electrons at all, and those are often called the highest occupied molecular orbitals, that is HOMO for short, or the lowest unoccupied molecular orbitals. That's the next available empty space. Because if my molecule is going to act as Lewis base, the electrons are going to come from these orbitals. If my molecule is going to act as Lewis acid, the electrons are going to go into these orbitals. And so therefore these are going to be key. These guys are collectively called the frontier molecular orbitals, or FMOs, and those are going to be important once we consider the reactions of these guys. They're going to be the most important ones to consider. All right, in our next presentation we're going to look at the reactions of conjugated pi systems. Our next video is going to specifically focus in on something called the Diels-Alder reaction, which is really the archetypical cycloaddition. All right, see you then. Thanks.